Our lab today is concerning buffers. Buffers are solutions that are mixed by preparing a solution that contains significant amounts of a weak acid in the same solution as significant amounts of its conjugate base. So for example here I have the weak acid carbonic acid. Carbonic acid is weak, it has two H's that it can give, but its conjugate base is different from the carbonic acid by the difference of just one of those H's. So if I take a proton away from the carbonic acid, the proton being a hydrogen ion, an H and a plus charge away from the carbonic acid, I produce the conjugate base of carbonic acid. If I have just the conjugate base in solution, in order to appreciate what its conjugate acid is, you simply add the proton to the conjugate base. You include an H and a positive charge. So minus an H plus to produce the conjugate base, plus an H plus to produce a conjugate acid. So that way you can recognize conjugates when they are together, if you're just trying to write a conjugate for an acid or a conjugate for a base. Now, to make a buffer solution, those two substances have to be in significant comparable amounts to each other. So imagine I could create a buffer solution. One way to do that is to take a solution that's 0.1 molar in carbonic acid and then dissolve up a solution that contains a bicarbonate ion, like sodium bicarbonate contains a bicarbonate ion, and dissolve it in that same solution until the concentration of bicarbonate is significant compared to the carbonic acid. In this example, I've made them equal concentration, but a buffer doesn't have to be equal. They can be unequal, but they do have to both be significant. Now, what's the point of this? The point is that a buffer solution resists change in pH. So if I add small amounts of acid or small amounts of base to my solution, I will see that the pH will change, but not by a lot. It will buffer the effect of the acid or the base. So why does that happen? Well, it happens because in the solution we have something that acts acidic and something that will act basic. Because a weak acid produces a conjugate base that is actually a base, then it will be able to neutralize small amounts of added acid because it has a base, and small amounts of added base because it has an acid. These two reactions up here demonstrate that. If I were to add a base to my buffer solution, remember the buffer solution contains both the acid and its conjugate base. So here's the weak acid. The weak acid will effectively suck up the extra added base as long as it's just a small amount, and it'll neutralize it. See how it happens? The hydroxide will take a proton from the acid, producing the conjugate base of the carbonic acid and water. So the base is a proton acceptor. It accepts the proton off of the carbonic acid. And so the carbonic acid effectively soaks up that base and neutralizes it, takes it out of affecting the pH. So the pH will be affected, but it'll only be affected a small amount as long as I don't add a ton of the hydroxide. Conversely, if I add acid, the H plus ion here is representing the acid for us. If I add acid, I have the presence of the conjugate base. The conjugate base is a proton acceptor. So it takes that proton and adds it to its formula and produces its conjugate acid, carbonic acid. Now because this acid is weak, this conjugate acid will stay together. It won't ionize very well, and that makes the reaction go to the right. If this acid were strong, this wouldn't work, and you can't make a buffer then out of this solution. You would just have a solution with a strong acid and its conjugate base, and it wouldn't be a buffer. So how do we know what the pH is going to be? And what we have to do is go back to the weak acid equilibrium, written for carbonic acid. So carbonic acid is a proton donor. It donates its proton to the water. That produces the conjugate base and hydronium ion. Here is the equilibrium constant expression for this equilibrium. It's called a Ka, a weak acid equilibrium expression. So we have the conjugate base times hydronium ion over the conjugate acid. So we start here. Now remember, in the buffer solution, I have significant amounts of both of these reagents, the conjugate base and the conjugate acid. To come up with an equation that will describe the effect of the pH on the buffer solution, we take a logarithm of this equation. Now I'm not going to go through the whole derivation, I'm just going to show you the result of that logarithm. The pH is going to equal the pKa plus the log of the ratio of the conjugate base concentration on the conjugate acid. So this is called the Henderson-Hasselbalch equation. And all it is it's the logarithmic form of the Ka expression. So you can see you can see where the logarithm comes from. We know that the pH is the negative log of the hydronium concentration, and that's commonly used to describe how acidic a solution is or how basic a solution is. The pKa then is going to be the negative log of the weak acid equilibrium's Ka value. So let's say the Ka value is 1 times 10 to the minus 6, just for an easy example. We know that the log of 1 times 10 to the minus 6 will be negative 6. You can try that out for yourself on your calculator if you want, or you can simply see that the exponent here is a negative 6, and then a negative of the log will give you a plus 6 for the actual pKa value. So let's say that we had the weak acid and conjugate base, and we were trying to solve for its pH based on these concentrations. So the pH would equal the pKa plus log of the ratio of the base concentration, the conjugate base concentration, over the acid. Substituting in the pKa value as 6, you would have the log of the base as 0.1 and the acid as 0.1. Now what's 0.1 divided by 0.1? 1, right? Of course. The log base 10, or any base, of 1 is equal to 0. So when the two concentrations are equal, the conjugate base and the conjugate acid, your pH will equal the pKa. All right? Now let's say we change that concentration, because again, they don't have to be equal concentrations to produce a buffer, but they do have to be significant compared to each other. Let's say we made the concentration of the acid equal to 10 times that of the base. Okay, so in order to calculate the pH, we would have pKa. In this case, we're going to keep our pKa at 6 just to make our example easy. We'll have the acid as being 10 times more than the base. All right, it doesn't matter exactly what the concentration is, since this is a ratio. If the concentration is 10 times more than the base, this ratio will reduce to 1 over 10. So if you take the log of 1 over 10, that's the same as 10 to the minus 1, so that log is going to be minus 1. And this pH, you can do it in your calculator if you want, this pH will be 5. Okay? Conversely, if the base is 10 times the acid, the way you set it up in Henderson-Hasselbalch is that the pH will equal, we'll stick with the pKa of 6, plus the log of base over acid. Now your base acid ratio is 10 over 1. Because we have 10 times more concentrated base than acid, so the ratio will be 10 to 1. The log of 10 is equal to 1, so in this case your pH would be 7. So as this ratio changes, the pH does change, but it will be buffering compared to if you put the acid or the base in water alone without the presence of the conjugate base and the presence of the conjugate acid in order to neutralize them. Okay, we're going to be testing pH by using universal pH paper. Take a look at the scale for the color, and the pH is here. I'll show it to you again as we move through. We're going to test, first of all, 0.1 molar hydrochloric acid. So we'll put it into this spot plate and then use the pH paper to test it for its pH. So the pH paper normally looks like this. We're going to dip it into the well plate, and then you can look at the color and tell me what pH you think that is. Next in line is acetic acid. So that was hydrochloric acid, this is acetic acid. Using the paper, we'll dip it into the solution, and you can check its pH by looking at this color and comparing it to what you see on the chart. The next solution is sodium acetate. Sodium acetate is the conjugate base of acetic acid because it contains acetate ion. So let's take a look at the pH of sodium acetate. Dipping it in and comparing on the chart. Okay. Next one up is carbonic acid. Once more, taking the universal paper, it's like Scotch tape. I can't find where the, there it is. There it is. Here, let's do a refresh here. There's a nice piece. This is carbonic acid. It's kind of bubbling like soda pop, which is kind of interesting to see. And again, take a look at the paper and the chart. And do your best. All right, next up, we have sodium bicarbonate, which is the conjugate base of carbonic acid. Let's see what it looks like. Ooh, interesting. Match it up. And again, remember, visualize this as the conjugate base of carbonic acid. Now let's try the next in line. We have ammonia, NH3. Let's see what that ends up being. There we go. Oof. Take a look at that and determine what its pH must be. And then finally, I think this is the end of the line. Yes, sodium hydroxide. Putting the paper in the sodium hydroxide produces this color. Whoopsies. There we go. So look at the chart. Determine what the pH, approximate pH of the sodium hydroxide solution is. This is a pH meter. The pH is read here. This bulb is the detector end of the pH. It consists of a glass bulb, and it's able to read the conductivity of solutions and convert that into a pH level. In fact, it specifically responds to hydrogen ions in that conductivity. So the pH meter does need ions in order to make a good reading, so it doesn't work in pure water particularly well. And it also only works well for substances that are not on the extreme ends of acidity and basicity levels. So we're only going to be testing the same solutions that we did last time that are not on those extreme ends. So the middle 5 solutions that we did are going to be retested looking at the pH with this pH meter. Down here is a buffer solution that you store the pH meter in because the bulb needs to be hydrated in order to work effectively. And you can see that that buffer is at a pH of about 4. Okay, so let's take a look at the solutions that we tested previously with the universal paper. And the first one that we're going to test is the acetic acid. So looking at the acetic acid, you should be able to see the pH value for it and record that. Let's see, it's kind of stabilized now. Okay. Now in between, to properly use a pH meter, you do need to rinse the bulb off to get any of the preceding solution off, and then carefully wipe the bulb with special chemical white cloth called a Kim-Wipe. Okay, the second solution then is the sodium acetate. So we're looking at the conjugate base of acetic acid. So let's see what its pH value is. And it's looking like not quite stable yet, so hang in there. And you should be able to see it now, fairly stable. If it drifts a little bit, don't sweat it. Just write down a value that looks pretty stable or close to it. And we'll move on to the next substance. Okay, our next substance is carbonic acid. So let's get ready for carbonic acid. There's our value. Wait for the pH meter to come to a stable value. Oh, it's pretty stable right there, I think. Take your pH reading. That's carbonic acid. And then the next one is sodium bicarbonate, which is the conjugate base of carbonic acid. Take a look. Still drifting around a little bit. That looks pretty good. So that's sodium bicarbonate. All right. Last one is the ammonia. We won't be testing the sodium hydroxide or the hydrochloric acid because they're too acidic on one end and too basic on the other for the pH meter. All right, there's the ammonia. It's fairly stable. Yep. So take your reading and enter that in, and then you can compare those to what you estimated using the pH paper. Now finally we're ready to go into the actual buffer portion of this experiment. In the first one, we're going to create a buffer that consists of the acetic acid and sodium acetate. If you look at this is buffer A, so I have my beaker labeled A, and we're going to add 5 milliliters of the 0.1 molar acetic acid to 5 milliliters of 0.1 molar sodium acetate. What that will do is it will produce a solution that has the same concentration of acetic acid as sodium acetate. They will be equal. So that will be a 1-to-1 ratio in the Henderson-Hasselbalch equation. So let me measure out 5 of the acetic acid into beaker A. Then five milliliters of the sodium acetate also will go into beaker A. Okay, so that's buffer A. Buffer B, we're going to do the same thing. So sodium acetate and the acetic acid, only this time we're going to change the amounts that we're using. So for buffer B, we're only going to put 1 milliliter of the acetic acid into the beaker. Make sure I rinsed out my graduated cylinder. And I'll measure out 1 milliliter of the acetic acid. That's going into beaker B. Rinse that out, and then we're going to put in 10 milliliters of sodium acetate. So here's my sodium acetate. I will add 10 milliliters to beaker B. Now, if you'll notice, then that is going to give you a 10-to-1 ratio of conjugate base to conjugate acid, because the two concentrations are the same, but we're adding differing volumes. A 10-to-1 volume, so it will be 10 for the conjugate base and 1 for the conjugate acid in this ratio for buffer B. Okay, so that's buffer A and buffer B. Similarly, we're going to mix up buffer C using carbonic acid and sodium bicarbonate. So here is my carbonic acid. The first one will be 5 milliliters each of carbonic acid and sodium bicarbonate. So that's going into beaker C, 5 milliliters. Then the sodium bicarbonate will also be 5. So in this case, I'm making a buffer that has a 1-to-1 ratio of conjugate acid, conjugate base. They're both the same concentration, and they're both going in at the same volume. So that ratio of conjugate acid to conjugate base will be 1-to-1 for beaker C. And then finally, beaker D. We will stick with the same buffer, but we're going to differ the ratio. This time we're going to have 1 milliliter of the carbonic acid. So in both cases, we're going to have a 10-to-1 base over acid ratio. So there goes 1 milliliter of the carbonic acid. Put that away. And then 1 milliliter of our conjugate base, or I'm sorry, 10 milliliters. So that will be a 10-to-1 ratio of the base compared to the acid. Well, let's see what happens when we measure the pHs. Okay, so here's our 4 buffers, and we're going to measure the pH of each of the buffers without anything added to it. So here's our pH meter. Got to do the old rinsing and wiping. And here is buffer A. So there's your pH. That's for buffer system A. For B, with the 10:1 ratio, there's your pH. See if this one looks good, nice and stable. Okay, buffer C. This is the 1:1 ratio of the carbonic acid to sodium bicarbonate. C, and then finally D with the 10:1 ratio of bicarbonate to carbonic acid. Let's see what that ends up being. All right, so that was the buffers with their differing ratios of conjugate acid to conjugate base. Okay, I've divided up each buffer in half, and to each of the buffer systems we're going to add some acid to one half of it and some base to one half of it. So this is the buffer A. So for buffer A, I'm going to add a 1/2 milliliter, that's 10 drops, of hydrochloric acid. To 1/2, and then 10 drops of sodium hydroxide to the other half. Now let's see what happens to the pHs of each of those. So this is buffer A with 10 drops of hydrochloric acid. Make sure that the bulb is completely submerged as well as we can. That's pretty good, I think. And there's your reading. And buffer A with sodium hydroxide. Okay. Now let's do the same thing with buffer B. I have my 2 cups here. To one I will add 10 drops of hydrochloric acid. To the other, 10 drops of sodium hydroxide. And let's see what happens to the pH. So this is buffer B with the hydrochloric acid. And this is buffer B with the sodium hydroxide. Okay, moving along. Buffer C's turn. So for buffer C, once again, 1/2 ml. Hydrochloric in one, and sodium hydroxide in the other. Alright, so let's see what those pHs are going to be. Okay, so this is buffer C, hydrochloric acid. There's your reading. And buffer C with the sodium hydroxide. All right, last one. Let's add our 10 drops of hydrochloric acid to 1/2 of it. And then get these guys out of the way. This is buffer D. 10 drops of hydrochloric acid and 10 drops of sodium hydroxide. Out of here. Fun times. Okay, so let's take a look at the pH. So here's the buffer D with hydrochloric acid. Looks like it's shifting a little bit. Let's wait a second. So I wish this was just a little bit deeper. I think that's pretty good. And then buffer D with the sodium hydroxide. Okay. Now, so we saw that the pH did change. So how well did our buffers work? Did they actually resist change in pH? So what we're going to do then is take regular plain water and we're going to add some hydrochloric acid and some sodium hydroxide to just plain distilled water in equivalent amounts and see how water resists change in pH, or if it does. So here is plain distilled water. Now, taking the pH of plain distilled water doesn't work well because you need dissolved ions in the water in order for the pH meter to work. So we're going to assume that the distilled water is just going to have a pH of 7. It should, right? So now we're going to add hydrochloric acid to the distilled water. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's see what the pH is going to look like. Remembering that distilled water is going to start with a pH of 7. Okay, interesting. Now let's try that with sodium hydroxide. So we will get yet another sample of distilled water, 5 milliliters, just like we used for the buffers. And add 10 drops of sodium hydroxide. Again, can't directly measure the pH of the distilled water, but we know that it starts at a pH of 7. So here's the sodium hydroxide. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 drops. That's half a mil. And here comes the pH meter. So let's see what happens. And there's your pH. Okay, and that is the experiment on buffers.